We chose this topic because we wanted to explore a driving question of how density affects objects in water. We explored different materials and objects we could use to make a boat. We first found how buoyancy was discovered and came across a very interesting story. The story goes that Archimedes, a famous Greek scientist, was given the task of determining whether the king's golden wreath, a gift of the gods, was made of real gold or some alloy. Archimedes wanted to melt the gold material into a known volume and weigh it, thus determining the density. But the king would not allow this, so Archimedes thought about this for some time until one day while bathing, he noticed the water level increased as he entered the tub, proportionately to his volume. This meant that he could put the difficult-to-measure crown in water and instantly know the volume of the crown by measuring the displacement of the water. At this point, Archimedes leapt up from the tub and ran naked through the street shouting, "Eureka! Eureka!" What Archimedes came up with was a relationship between the volume of a solid and the volume of a fluid, which directly relates through the density equation to a relationship between the density of a solid and a fluid and the mass of a solid and a fluid. He also determined that the buoyant force, the mass of an object out of the fluid minus the mass of the object in the fluid, is equal to the weight of liquid displaced by the object, or mass out of fluid minus mass in fluid equals density of fluid times volume of solid, or even easier, buoyancy equals P times V. So within that story, we found that buoyancy is described as a force. Just as gravity, drag, and acceleration are all forces that move you in one way or another, buoyancy moves a body in a direction which happens to be up. This upward force occurs only when a few criteria are met. First, you need to be in a fluid. This can be a liquid or a gas, some medium with moving electrons, but not a solid, as the electrons are held too closely in place. The other requirement is that the fluid has to have a measurable density. We explored density in class when we were exploring hot air rising and cool air sinking. When air is heated, the molecules get excited and want to move further away from each other, which creates a less dense air mass, causing it to move up. As for density in objects, we know that density equals mass divided by volume, which was key information in our research. The last bit of research we did was looking at the density of some common household objects to make boats out of, and went through the experiment from there.
Boats have been around for centuries. One of the earliest boats was built in 3000 BC in the first two civilizations, Egypt and Mesopotamia. They used their boats to travel on and through the Nile River. They would use wooden oar boats with a large rectangular sail. They would use the sail to go upstream and use the oars to travel back down the river. Over the years, boats have been used for many different things. Depending on their use, they are constructed of different materials. One thing that we use boats for today is our military use. Navy boats today are made out of steel alloy. This is used because it is strong enough to fight off enemy attacks and keeps the boat floating. Another thing that we use boats for today is to transport goods. Cargo and container ships are usually made out of materials like steel, aluminum, fiberglass, or plywood. Depending on the boat or ship is used for, the materials may vary. Just like the materials may vary, the density of the ship varies depending on what type of boat or materials are carried in the boat. From early wooden boats to our giant steel and various materials of ships now, there has been a lot of progress made to better the system of transportation, but we believe that there is still more progress to be made. We covered both core standards and Indiana state standards for this learning experience. The core standard that we covered in this experiment was design a moving system and measure its motion. The Indiana state standard that we covered for this experiment was 4.4.4. Define a problem in a context of motion and transportation. Propose a solution to this problem by evaluating, reevaluating, and testing the design. Gather evidence about how well the design meets the needs of the problem. Document the design so that it can be easily replicated. For this experiment, we thought it would be best suited for a 4th grade classroom. This not only matches up with their standards, but it is also a high enough learning experience to expand their knowledge and a low enough learning experience for them to be able to complete the experiment.
Before beginning our experiment, we looked at the density of common objects as well as the objects being used in our experiment. After closer examination of these numbers, we realized that there is a wide variety of differences in the density of these common objects. One density we looked at was that of a brick, which is 1.84 grams per centimeter cubed, and the density of a gold bar, 19.3 grams per centimeter cubed. Even though we knew neither would float, a brick's density is less than a gold bar, so we can assume the gold bar would float better than a brick would. We also looked at the density of each substance we tested. After having that data, we created boats which were 4 by 4 by 2 inches out of modeling clay, popsicle sticks, a plastic bottle, paper, aluminum foil, and cardboard. We then began our experiment of testing how well each floated and how many quarters it took to sink the boat. The first boat we tested was made out of modeling clay. To create the boat, no other materials were needed. The clay was simply formed in the shape following the measurements. Clay has a density of 2 grams per centimeter cubed. It held 17 quarters and had no visible leaks when it sank. The next boat we worked with was created from popsicle sticks. To help hold the sticks together, we used glue from a hot glue gun. This also helped close any gaps that could otherwise be found in between the sticks. The popsicle sticks had a density of 0.67 grams per centimeter cubed. After holding 15 quarters, the boat sank. The hot glue did create seals, but they were not exact and allowed water to come in. The next material we tested was plastic. We used a plastic bottle with a density of 1.38 grams per centimeter cubed. We cut the bottle up and used hot glue to create a boat following the proper measurements. The boat took on water after only 2 quarters and then it sank. We realized the seals on the boat were not done properly, which allowed water to seep in. We then tested a boat made out of paper with a density of 0.7 grams per centimeter cubed. The boat was able to hold 27 quarters, but the more quarters that were added, the more water the boat absorbed. We then tested aluminum foil, which has a density of 2.7 grams per centimeter cubed. The boat was able to hold 13 quarters before breaking simply because of the weight. The last material we tested was cardboard with a density of 0.7 grams per centimeter cubed. It held 35 quarters before sinking. We used hot glue to put the pieces together. The boat took on water after only 20 quarters were put into it, but it was able to hold more because it was sealed well and also was slightly larger than the intended measurements. From our experiment, we were able to conclude that the best-made boat, after taking in the measurements, the amount of quarters held, and the seals, was the boat made out of clay. It held up throughout the experiment and also has a high density. It sunk simply from the amount of weight in it.
Our first consultant was Dr. Jessica Weller, continuing our lecture of chemistry at Purdue University. We communicated with Dr. Weller through email since our meeting with her had to be canceled at the last minute. We sent Dr. Weller questions about density and how density would affect a boat's ability to float. She responded to our email by sending us a link to a chemistry lesson plan that talked about what density was, the density of materials like the ones we used in an experiment, and the density of water, and how density from the chemistry standpoint can affect a boat's ability to float. After reviewing a couple of lesson plans off of www.middleschoolchemistry.com, we learned a lot about density, like density equals mass of a substance divided by the volume of that specific object. After learning the basics about density, we figured out that density of an object or a certain type of material is what determines whether or not the object will float or sink in another substance. If you place an object in a liquid like water and it floats, it means that the density of the object is less dense than the water that it is sitting in, and if the object sinks, the object is denser than the liquid it is sitting in. For aluminum, the molecules look like they are so close together, and some look like they may be overlapping. For plastic, the molecules look close together, but instead of being stacked, the molecules are in rods and that are close. For wood, the molecules are close together, but there is a gap between the group of molecules in the middle. As a conclusion, the lesson ends by talking about how these materials, wood, plastic, and aluminum cubes, might have the same volume but have different masses, which are based on the structure and arrangement of the atoms and molecules of each material we used. From a chemistry standpoint, the best materials we can use to create a boat and hold the most quarters would have to be less dense than the water it is going to be in. The lesson plans that Dr. Willis sent us really helped us understand density more. It helped us understand how density of a boat and the materials and the weight of the people have to be less than the water that the boat is in. From all of this, we have a deeper understanding of density, but we want to know more about how the boat is constructed and what is the most efficient way and materials to be used. The world today revolves around trade, and there are many different ways to transport goods, but the most important way to transport goods around the world is by boat. Boats are a unique way to transport goods since most of our planet is covered by water. By doing research on how density affects boats, it can help engineers and designers to construct boats that are efficient and use the least amount of materials with the very least amount of waste.
Our second consultant was Dr. David Koltik, Professor of Physics Director and Applied Physics Laboratory Coordinator. Dr. Koltik received his Ph.D. in physics from the University of Michigan in 1978. One of his major research interests includes fundamental forces of nature. He also has extensive knowledge of sailboat operation and construction. During our meeting, Dr. Koltik addressed several misconceptions that we had when we formed our original hypothesis that density determines an object's buoyancy. He began the meeting by discussing the concept of buoyancy. He told us that buoyancy is a force pushing upwards on an object in the water. In order for an object to float, the downward force from the weight of an object must be equal to the upward force applied by buoyancy. He then explained to us that the density of the material used to create a boat is not the sole factor in determining whether the boat will float. The ability of a boat to float is mostly determined by the amount of water it displaces. The displacement of water, as discussed earlier, is known as the object's volume. In order to float, the boat materials and its cargo must weigh less than the amount of water it displaces. Therefore, the denser the material used to build the boat, the larger volume it will require in order to float. Successful boats are constructed to displace enough water to hold their weight without sinking. This is why, when we constructed a boat out of a more dense material such as clay, the boat still floated. This occurred because the clay displaced an equal or greater mass of water than it weighed in the tub. All of our materials eventually sunk when their weight applied a greater downward force on the water than the upward force of the water on the boat. This was due to the steady application of quarters. Therefore, the buoyancy of the different boats had less to do with density of the materials than we originally hypothesized. Finally, Dr. Koltik gave a brief overview of some other factors affecting the buoyancy of a boat that we had not yet considered. For example, he stated, "The center of gravity has a profound effect on the success of the boat. For a sailboat, the center of gravity must be under the water so that it won't tip over. For a boat like a pontoon, the center of gravity is above water, but it relies on the pontoons to balance its weight as the wind blows." From this consultant, we learned a great deal about the ability of heavy ships made of dense materials to float. Dr. Koltik addressed some of our key misconceptions about the factors that affect buoyancy and provided us with information to form new driving questions and experimental procedures if we were to complete this project again. If we were given the opportunity to work on this project again, there are many aspects of the project that we would change given the information from the experiment, research, and consultants. First, we might remodel our driving questions. For example, what relationship does displacement of water have to buoyancy? How can extremely dense materials such as steel float in the water? How do outside forces such as waves and wind affect a boat? What materials can be added to a boat to increase its ability to float? Next, we would change some of the variables in our experiment. For example, we might measure the volume of a rock by displacement of water and compare this calculation to the measured volume of a uniform slab of clay by displacement of water. We would then be led to the conclusion that though the rock is a heavy material, it displaces only a little bit of water. In other words, the rock has a small volume but a heavy weight. It will therefore exert a greater downward force on the water than the upward force of buoyancy. The rock would sink to the bottom of the tub. The slab of clay, on the other hand, would displace a larger amount of water. Its downward force on the water would therefore be less than the upward force of buoyancy. The slab of clay would float. Reflecting on our original hypothesis was an important component of finishing this project, as it led us to new driving questions and a deeper understanding of the concepts of density, buoyancy, volume, and mass and their cumulative effects on a boat's ability to float.